Okay, so we started a brand new section on probability. Probability, well, this is a statistics class, so of course we have to talk about this, right? And basically, probability teaches us about like, okay, how likely is something, right? I told you that probability is on a spectrum, right? So you can't have a probability like less than 0, and you can't have a probability more than like 1 or 100%. That doesn't make any sense. We also had some notation that we introduced. P in parentheses of something means the probability of, and so on. We talked about the sample space, which was not too important, but then I introduced this thing called a probability distribution. Whenever you hear the term distribution, all that's saying is like a chart or a graph. So whenever we're talking about a probability distribution, we're talking about a chart that lists all the things that can happen and then the probabilities underneath each of them, okay? Now, we did a little bit of work of creating probability distributions and determining if something was one, and now we're gonna like put it all together using these probability rules, okay? Now, before I talk about these rules, we introduced the idea of mutually exclusive. Is there someone who can describe what that word means, Raven?
It means that, for example, if you're teaching a class in here and teaching a class in here, you cannot be in both rooms at the same time.
Perfect, right? So mutually exclusive events, they can't happen at the same time. So like Raven said, I can't be in this classroom and I can't be in that classroom at the same time, right? Unless we like bust down the wall or something. But then I'd get fired and I wouldn't be teaching you. So, all right. So based on that word, we have 3 different probability rules. If we have things that are not mutually exclusive, so that means they can happen at the same time. If I want to find the probability of a combination of events, you just add together the probabilities and subtract off where they overlap. If they are, then you just add together the probabilities. And then I didn't explain the last rule. So let me show you this rule here. We have this event and it's A with a C on top of it, okay? What the symbol, how the symbol is read is we read this as A complement, okay? And it's not a compliment like, hey, Amy, I like your shirt. It's more a compliment as, if you ever heard of complementary colors on a color wheel, they're colors that are on the opposite sides of a color wheel. So when we talk about the complement of something in math, we talk about the opposite. So the opposite. Okay, so if we have an event, we just call it A complement is just the opposite of that event. So if I want to find the probability of an event, okay, it's literally just 1 minus the probability of the opposite event. Okay, so whenever we have opposites going on, if you want to find the probability of one thing, just subtract the other probability from 1. Let's put these into practice here, okay? Example 9, we have a card. We have a stack of cards actually, and all these cards are labeled 1 through 9. Okay, so there's 1 of each card. Okay, we draw a card from the stack and it's like randomly organized or whatever. Okay, first we have to construct a probability distribution. I think that will help us a lot here. So here we have all the things that can happen, like choosing a 1, a 2, a 9, and so forth. What's the probability that I choose a 1 out of the stack of cards? Perfect, right? Because if there's a total of 9 cards, well, 1 out of 9, right? And I guess choosing a 2 would be also 1 out of 9, right? And 3 would also be 1 out of 9, and 5 would be 1 out of 9. So this probability distribution is pretty easy because everything occurs at the same amount here. So all the probabilities are the same. Okay. Now, I'm just choosing 1 card out of this whole stack, and each of these cards just has 1 number on it. So is choosing like a 2 and choosing a 4, are those 2 things mutually exclusive? See some nods. Why are they mutually exclusive? Like, yeah, right. There's no card that has a 2 and a 4. So it's not like I can choose a card and have it both be a 2 and a 4. Okay, so the answer to this would be yes, because, well, these 2 things cannot happen at the same time, right? Can't happen at same time. Okay. Okay, now that we know this, it makes it easier for us to find the probabilities of things, okay? This question's asking us to find the probability that x equals 3 or x equals 4. First of all, let's take a look at our rules. Which rule do you think I'm going to use here? 1, 2, or 3? Is it 1? Yeah, I'm definitely using rule 2 here because we have mutually exclusive events. It says if I want to take the probability of A or B, I just add together the probabilities. So using the rule, technically what we're doing is we're just separating out each of the probabilities, 3 and the probability that x is 4, and it just tells us to add them together. We don't have to do anything, just add the two probabilities together. Well, what's the probability that x equals 3? 1 over 9, and then x equals 4 is also 1 over 9. So if I add together these two probabilities, we get perfect 2 out of 9. Awesome. Any questions on how I did this? Perfect. Oh, yeah.
So basically, you just follow this rule in with the x equals 3. Or this is the probability.
Yeah. So if you don't, I use this notation because this is how the rule uses it. If you just want to be like, okay, if it says or, you just add together each of these two probabilities. I'm not really expecting you to write this necessarily, but for some reason, it kind of helps me break it down using the rule and exactly what it says. Basically, what you do is you just add together the probabilities.
Okay.
All right, number C, we need to find the probability that x is an odd number. Now, that's not really like on the probability distribution, but I wonder if there's a way we can reword this question. Instead of saying odd, what's another way to say x is odd? Well, maybe we could just take the odd numbers and list them, right? Isn't this the same thing as saying x is 1 or 3 or 5 or 7 or 9, right? Yeah, so this is the same thing as saying x is odd, okay? Now, there's no rule that gives a bunch of different things, right? We only have a rule that says, okay, x is 3 or x is 4, and we can split that up into two things being added together. When we have a string of things, it's basically the same thing, okay? I know there's no rule that says A or B or C or D or E, but we can pretty much do the same thing. So how can we go about doing this question? Add them all together, right? So basically I can find the probability that x is 1, the probability that x is 3, the probability that x is 5. Oh gosh, I'm gonna run out of space here. The probability, you know what I'm gonna do? Let's just erase this, okay? I know the probability that x is 1 is 1/9. The probability that x is 3 is 1/9. X is 5 is 1/9, 7, and 9. And I'll just point to each of these probabilities here. I think that makes more sense. Okay. Well, when we add these together, we get 5/9. Is it 5/9? Oh, I wrote this wrong on my paper. That's okay. All right. 5/9 is our answer. All right, let's do something a little bit harder. This one asks us, okay, are the events x being 3 and x being odd, are those two things mutually exclusive? No, right? Because those things can happen at the same time, right? If I get 3, it's definitely going to be odd. And well, those two things happen at the same time. So this answer is actually no. Okay. These can happen at the same time. Okay. So why don't we go ahead and combine these together? In part E, I want to know the probability that x is 3 or that x is odd. We just said that these aren't mutually exclusive, which means we probably need to use rule number 1, right? Now, taking a look at rule 1, it says we need to add together the probabilities and then subtract off where they intersect or where they happen at the same time. To make this easier for me to understand, I'm just going to rewrite what the rule is telling me to do. This is telling me to find the probability that x is 3, add on the probability that x is odd, and then subtract off the probability that x is 3 and x is odd. Okay. Here's where things get a little tricky, okay? This probability, we have a situation where x is 3 and x is odd. What situation is that describing? Is there a way to like make that a little shorter, Nico?
Is it just like 1/9 because you have to pick up 3 in order for it to be 3 and odd?
Okay, yeah, that's exactly what I'm saying. So does everyone kind of understand what Nico's saying? Yeah, so is there any situation? Okay, if x is 3, then it's going to be odd, right? Are there any odd numbers that aren't 3 that would also count as x equals 3? Well, the only odd number is 3, right? So the only way we can have x is 3 and x is odd, the only situation where that's true is if x is 3, right? So saying x is odd, that's kind of redundant, right? It's useless to say x is odd if we already know x is 3, because the only situation this can happen is when x equals 3. So another way to write this is just the probability that x is 3. And there's no reason to say x is odd.
Right, it sounds useless.
Yeah, it's like a redundancy, right? It's something that is said, but it doesn't really matter because we already know what it is. Okay, well, let's go ahead and find these probabilities. The probability that x is 3, that's definitely 1/9, right? Okay. The probability, what is the probability that x is odd? 5/9, and what we got that from part C, right? So that's pretty easy. That's from part C. Okay. All right, and then the probability that x is 3 is still 1/9. Okay, so basically what we're doing is we're adding together the fractions of subtracting 1. Looks like this probability really is 5/9. Okay, so basically what we did is we found out that the probability that x is 3 or x is odd is really just the same thing as x being odd. All right, any questions on how I did part E? All right. Let's go to part F here. This is asking us to find the probability that x is not 5. The word not is in here. What do you think I'm going to use for this one? Rule 3, right? Whenever you have the word not or except or something that means an opposite, that's a good hint that we have to use rule 3, which says if I want to find the probability of something that's an opposite, I just do 1 minus the original event. Okay, so maybe another way to say this is the probability that x is not 5 is 1 minus the probability that x is 5, right? Not 5 and is 5, those are opposites, right? Well, I know the probability that x is 5, right? That's 1/9. Okay. Once we're here, we have two options, okay? One thing you can do is just change 1/9 to a decimal and do the subtraction. That is totally fine. But let's just do the fraction subtraction just because, well, I want to torture you a little bit. Okay, if we have fraction subtraction, the two fractions have to have the same denominator, right? That's the first thing that we want to do. I guess the same denominator would be 9, right? Because one of them's already over 9. How do I write 1 as a fraction over 9? 9/9, perfect. And when you subtract the two fractions, we get 8/9. Okay, so either way, if you just want to change it to a decimal, that's fine as well. This one's a little bit more precise though. Okay, before we move on, does anyone see another way we could have done part F? Nico?
You could just add it up everything but 9. The probability gave 1, 2, 3, 4, 5, 6, 7, 9.
Okay, I like that. So Nico said another way we could have done this is done this. Let's find the probability that x is 1 or 2 or 3 or 4 or not 5 or 6 or 7 or 8 or 9, right? Because these are the numbers that are not 5. Each of these individual events are mutually exclusive. We said that in part A and B. So another thing we could have done is just added 1/9 to itself 8 times, right? Okay,
Oh,
yeah. 1, 2, 3, 4, 5, 6, 7, 8. There we go. Okay, and you also would have gotten 8 nines. So whenever we have these not questions, they're actually you can do them without using rule 3 if you want to. The only thing that I would say kind of sucks about using this way is if there were like 100 data values, it would kind of be annoying to count up like 100 different data values, right? That would kind of be annoying, right? So I would say the left way is easier for me, but if you ever forget the left way, you can always do the right way. Okay. Any questions on example 9? All right, if we flip our page over, we have a very similar question. This is about a basket that has green grapes, yellow peaches, and green pears. You randomly select a piece of fruit. I'm gonna have X here represent the type of fruit that we get. Okay, so I want you to find the probability of grapes, peaches. I love grapes too, and pears. That is true.
Talking about cake.
Oh, I love should have done this the day I brought cookies.
I know.
All right, why don't you give this one a try? Very similar to what we did on the last page, and then we'll come back. All right, let's go up to the front here. Okay, so this example, we have green grapes, yellow peaches, and green pears. All right, I randomly select a fruit, so that's kind of the situation we're dealing with. The first question wants to know, like, if I get a grape or a pear, something like that, is that mutually exclusive? Cass, you want to explain this one?
I said it can happen at the same time because it says you were to select a piece of fruit, which is one. So you can't have two.
Yeah, perfect, right? You can't pick up a grape pear, right? I mean, I'm sure there's grape pears out there, but that's all right. All right, and Cass, do you want to explain how you got part B?
It's in the first rule because they're mutually, or second because they are mutually exclusive. You add the probability of them together,
Mhm.
which gives you 7 times.
Perfect. And then part C wanted to find the probability that we had just green. Who wrote that one? Was that Nico? Do you want to explain this one?
So the probability of them being green, the only 2 fruits that are green are grapes and pears, which means you're adding the likelihood of getting a grape or a pear, which is 3/10 plus 4/10 equals 7/10.
Awesome job. Next one I asked, okay, here's a different question. Is getting a green fruit and getting a grape, are those two things mutually exclusive? And why did you say no?
Because the grapes are green, therefore you pick up a grape, it's going to be a green fruit.
Perfect, right? These two things can't happen at the same time. All right, so part E was kind of the tricky one here, right? I want to find the probability that X is a green fruit or if it's a grape. Melanie, you want to take us through this one?
Yeah, so this is not mutually exclusive, so we use rule 2.
Mhm.
So I just did X equals green, which is 7 over 2, which we got from C, plus 3/10, which is just the probability for a grape, minus P green A grape, which is 3/10 because all the grapes are green. So that was 7.
Perfect job. All right, any questions so far? All right, skipping over, oh yeah, did you have a question?
How do I know that
Yeah, so the probability that something's green and a grape, let's think about that situation. If I have a grape, then it's definitely going to be green. So that's definitely in that green and grape category. But after we say that, is there any way like else that I could get a green fruit and it not be, well, if it was not a grape, then that wouldn't count, right? So I guess saying green here is kind of redundant, right? It's like, okay, green is kind of just extra on top of the grape. The only way you can have a green and a grape is if you pick a grape, right? Because those things are green. Yeah. All right. Yeah, it's kind of tricky when you start, but and these questions do get like even more complicated. In this class, it's kind of gonna stay with that redundancy for this question. So I wouldn't worry about it too much. It does get way more complicated in the future though. So we'll just kind of close our eyes and forget the more complicated parts. All right. The last one, we want to find the probability that X is not a pair. How did anyone do this question? Melanie or I'll do Melanie.
So I did it both ways since we like only did it for rule 3 and rule 1.
Mhm.
So for rule 3, for rule 3, it was 1 minus p as its pair, so that's 1 minus 4 over 10.
Mhm.
And to subtract it, we would just change 1 to 10 over 10,
Mhm.
and then it would be 6 over 10. And then, it would just be 3 over 10 plus 3 over 10 because
Mhm.
that's the probability of the rate of each.
Mhm.
Which is not a pair. So it'll just be 6 over 10.
Awesome. So I kind of just wrote what you were talking about as you were saying it. Two different ways we can go about this, either subtracting from one or just adding together everything that fits the description. Really nice job there, Melanie. All right. Any questions on these probabilities? All right. I will say finding probabilities and combinations of them, these get super duper complicated. There's like a whole section of math where we combine different things, where we have different situations and we're trying to find like intersections between a bunch of them. I'm going to say it just gets more and more complicated. So I'm not even going to go into that too much just because, well, it just gets more complicated as we go on. But yeah, this is how complicated we're getting here. All right. I'm just going to introduce the next topic and leave it at that. Next class, we're going to start with the probability histogram. It's not too bad. It's basically the same situation as we've been doing with before. It basically, instead of looking at a probability distribution as a chart, we're going to take a look at it as like a bar graph or a histogram. So that's kind of the direction that we're headed. I think you guys need a little break because of daylight saving time. So let's just end class early. I think